All right, welcome back, everyone. So the plan for today, it's a special day today. Now, I'm going to start, well, it's not so special, but it's a cool lesson. I'm going to start with 1.3, which is a really great, fun lesson about the gallery of graphs, all right? So section 1.3, I've about an hour of videos on that, okay? And then I'll address some general questions you might have about the homework turning in. And then we might want to take a 10-minute break to gather our thoughts. You can gather your stuff, right? Maybe your notes, your homework. And then after the break, we can address any number of questions. By the way, it's been my experience that students are okay with recording, but if for some reason you don't want the recording, let me know. Or if you don't want me to say your name, chat at me in private. But the recordings have gone well so far. It's good to have that record. And the homework is due tomorrow, Friday. We can talk more about that after, just before the break. All right. So any questions before we start 1.3, about an hour on that? Any questions? We're now recording. I gotta mute everyone. Okay, unmute is necessary. All right. All right, so, okay, let's go ahead and start section 1.3. It's a fun section. It's one of my favorite ones. And it'll save you time. Here we go. Hi everyone. Today's the 3rd. Hi everyone. Let's do section 1.3 on basic graphs and symmetry. Oh, we're going to prevent you from having to. This is. It looks like the closed captioning didn't catch on this one. Hold on a second. Yeah, sorry. It looks like the closed captioning didn't catch on this one. Maybe Zoom will catch it. All right. Hi, everyone. Let's do section 1.3 on basic graphs and symmetry. We're going to prevent you from having to do too much point plotting, so these will be your friends. It will be good for you to learn a basic gallery of graphs, and symmetry is your friend. It'll save you time when graphing. In particular, we're going to graph a lot of power functions. Functions whose rules look like f of x equals x to the n, where n is some real exponent. In fact, by the end of this section, you should be able to graph anything of the form y equals x to an integer. Now, the first functions we're going to look at can be thought of as some basic examples of these, maybe. What are some examples of very lazy functions? Functions that aren't very creative with their outputs. What are some very basic lazy functions? Why don't we start off with constant functions? F of x equals c, where c is some real number, like 3. Take f of x equals 3. Well, how would you graph the line y equals 3? It's going to be a horizontal line. Here's a graph of y equals 3. This graph represents the function 3. Notice it passes the vertical line test. This is a function. Now, people might say, well, is it really a function of x? I mean, it doesn't really depend on x. Well, that's a semantic issue. Still, we say that f here is a function, even though x is not involved with the rule here. Another way you can see it's a constant function is that whatever the input is, 6, -10, whatever, the output's going to be 3. So the input could be 1 and the output is 3. The input could be pi and the output is 3. The input could be -3 and the output is 3. Every real input will yield the same output, 3. So that's an example of a very lazy, uncreative function. What's another example of a lazy function? And I'll give you a hint. Group work, where you do a bunch of work and you pass it on to somebody. That person might just copy your work. Hopefully not. But let's talk about identity functions. All right. Basically, an identity function has the form f of x equals x. Why is it called the identity function? Because the output is identical to the input. Whatever the input is, that's what the output's going to be. So if you give your partner 6, your partner spits out 6. Doesn't do anything. If you give your partner 10, your partner spits out, negative 10. If you give your partner negative 10, your partner spits out negative 10. Basically, this function is not doing any work. It's just passing on what you give it. That's an identity function. How do you graph y equals x? Or x to the first? It's a very basic example of a power function. Well, you graph y equals x as the slanted 45-degree line. If you input 1, you output 1. If you input 2, you output 2. If you input negative 1.5, you output negative 1.5, and so forth. If you input 0, you output 0. This is an odd function, as we'll see later on. Why do I use the plural? Because technically, the domain could be restricted. It doesn't have to be all real numbers. We're going to assume for now that the domain is R, all real numbers. Another lazy function. Now, this here is also an example of not just a power function, but a linear function. Okay? In general, we have a linear function if we have something like f of x, or it could be g of t or something, but f of x equals mx plus b, where m is the real slope and b represents a y-intercept. It's a real number that represents a y-intercept. Where m is not 0. If m is 0, you're just left with what kind of function? A constant function. And then you're back to this horizontal line here, right? That kind of horizontal line. So for a bona fide linear function, we assume that the leading coefficient m is not 0. And we saw a lot of these in section 0.14. Remember? We graphed a whole bunch of lines. So for example, if you have f of x equals 2x minus 1, well, how do you graph y equals 2x minus 1? Okay. You'd graph it as this slanted line here. So again, the identity function is an example of a linear function, but there are many more. Next up, we're going to look at some nonlinear functions and ideas of symmetry. Okay, yeah, again, the CC was off here, but any questions? These are basic examples of functions. We're graphing basic functions. All right. Hi, everyone. Let's talk about the squaring function with domain R. The rule given by f of x equals x squared. Domain is all reals. This is a good example of an even function. We'll talk about symmetry here later on. Well, if you don't know how to graph y equals x squared, do some point plotting. The domain is all reals, so let's plug in various real values for x, probably integers, right? The square of 0 is 0, so the origin, 0, 0 is on the graph, over here. Over here, the square of 3 is 9, so the point 39 appears on the graph. That's over here. But also, the square of negative 3 is also 9. So the point negative 39 also appears on this graph over here. And we see this kind of symmetry. If the point, I'll do this in green. Oh, whoa, sorry. Hi, everyone. Why do we call... Whoa. Hi, everyone. Square of 3 is 9. So the point 39 appears on the graph. That's over here. But also, the square of negative 3 is also 9. So the point negative 39 also appears on this graph over here. And we see this kind of symmetry. If the point, I'll do this in green. If the point x comma y lies on this graph, then that means that the point opposite of x comma y will also lie on this graph. So the graph of this function, which is an even function, will exhibit this symmetry about the y-axis. The graph of y equals x squared is symmetric about the y-axis. That's true of the graph of any even function, such as this one. Something else you should know about the x squared function, remember that squares of real numbers are never negative, which means that the outputs are never negative. The y coordinates are never negative. So the graph never falls below the x-axis. Again, every point x, y in the graph has a mirror image partner about the y-axis, opposite of x, comma y. This demonstrates the symmetry about the y-axis. Let's prove that algebraically. Why is this squaring function an even function with that kind of symmetry? A function f is even if and only if, and remember, this is going to describe symmetry about the y-axis, where y is a function of x. We're going to assume throughout this section that y is a function of x. A function f is even if and only if, well, when does this happen? If f of opposite x equals f of x for all x in the domain of f. So in other words, anytime you have an x coordinate where we have a point on the graph, here the domain is all real numbers. So we have points with all real numbers as x coordinates, all right? But every time you have an x coordinate in the domain, you're going to get a point on that graph. And then at the opposite value of x, you're going to get another point with the same y coordinate. Okay, for all x in the domain of f, okay, at opposite x, you get another point with the same y coordinate. Again, for all x in the domain of f, you get a point with a y coordinate, and also at his partner, opposite of x, you get the same y coordinate. So for example, at x equals 3, we got a function value that was positive 9. But at x equals negative 3, we got that same function value, or y coordinate, of positive 9. Opposite x coordinates in the domain yield the same y coordinate. And by the way, in order for these pairs of opposites to exist, we do need the following to be true. The domain of f must be symmetric about 0. That's to ensure that for every x coordinate in the domain, its opposite will also be in the domain. So in order to have an even function, the domain must be symmetric about 0. This statement kind of assumes that property. So let's quickly go over the proof of this. I wouldn't expect you to do this now, but later on in section 1.7, maybe. Let's prove algebraically that the scoring function on R is an even function. Again, we're assuming the domain is all reals. If the domain is not all reals, then we may not have symmetry. This here would not represent an even function if you restrict the domain. For all x in the reals, the domain of f, okay, here's the idea. You're going to ask, what's the deal with f of opposite x? So when you see something like f of opposite of x, the key word here is substitution. What happens when you substitute opposite of x, or negative x? A lot of us say negative x. What happens when you plug in opposite of x, or negative x, into x over here? You get the square of opposite of x. See, over here, f takes x and squares it. That's the basic rule. What does f do to the opposite of x? Well, again, it squares the input, the argument, the opposite of x. But the square of opposite of x takes us back to x squared, the same expression we got over here. Or its equivalent. Of course, x squared is equivalent to itself. So notice that the function values at the opposite of x and x will be the same. We get x squared in either case. F of opposite of x is equal to f of x for all x in the reals, the domain. Which means that by this definition, the function is even. The function is even. This is the official way to end a proof, QED. It's Latin for this. I won't pronounce it. That often denotes the end of a proof. Some people will use 3 dots like this. Fans of the band Rush will appreciate that. Okay. Or some books use a solid box. Okay. But QED is the nice Latin you can use. Once again, why is this scoring function even? If we replace x with its opposite as the input, we get equivalent outputs. We get x squared, that is f of x in both cases. For example, 3 and negative 3, x and the opposite of x give us the same function values, the same y coordinates. F of opposite of x over here, the y coordinate here, is equal to f of x over here, the y coordinate here. These are equal. Busy picture. Okay, so why do we call these even functions? What are some other function rules that'll get us even functions, where the domain is all reals? We have f of x equals x the second, and what else? Including some guys we saw before. All right. Any questions about even functions? Graphs symmetric about the y-axis. All right, we'll talk more. Once again, I don't know why the closed captioning is failing. Again, the Zoom should be able to pick it up. Hi, everyone. Why do we call these even functions? These graphs that are symmetric about the y-axis. Why do we call these functions even? Well, the kinds of functions that lead to these kinds of graphs with that kind of symmetry, they might be of the form f of x equals x to the second, and what else? F of x equals x to the fourth, x to the sixth, and so on. For that matter, x to the 0, which is basically what? This is basically 1, which is a constant function. Turns out there's a hole over here. We'll talk about him. And even something like x to the negative 2 and x to the negative 4. We'll talk about those. But it turns out that all these function rules, assuming that we're dealing with the implied domain, which would be all reals for these guys here, these are all going to be function rules for even functions with graphs that are symmetric about the y-axis. Let's talk more about these guys over here. F of x equals x to a positive even exponent. Their graphs will look like bowls, like these. Y equals x to the fourth, sixth, eighth, and so on. Their graphs will look like bowls. Let's go to Desmos. All right, so let's graph y equals x to the second. That's called a parabola, by the way. And then y equals x to the fourth. Now, technically, this is not a parabola. Only quadratics graph as parabolas. But still, y equals x to the fourth in blue here is still a bowl shape. And notice it does not fall below the x-axis because x to the fourth is never negative for real values of x, just like for squares. So we have two bowls here. Notice they're both symmetric about the y-axis. And not surprisingly, the blue parabola, y equals x to the fourth, out here is climbing more steeply than the red parabola, y equals x squared. So it's not surprising, for example, that, by the way, we're considering f of x equals x to the n, where n is an even positive integer for now, right? Although this is going to be even where n is any even integer. F would be an even function, right? But going to these guys here, so if we have x to the second and x to the fourth, right? Well, it's not surprising that if you take x values like 2, 3, and 4, it's not surprising at all that the fourth powers of those values will be greater than the second powers of those values. That's not a surprise. The fourth power of 3 is a lot more than the second power of 3. Okay, so it's not a surprise. It's not a surprise that the y-coordinates on the blue graph are higher than the y-coordinates on the red graph. But if we zoom in, we may be getting more of a surprise once we zoom in. Take a look what happens. Look at this. This might surprise you. If we zoom in close enough, close to x equals 0, specifically between -1 and +1, notice that the blue graph actually lags below the red graph. And that might surprise you, because you look out here and go, oh, the blue graph's above the red graph. Well, if you zoom in, you'll find that the blue graph does dip below the red graph over here. And in fact, in calculus, you're going to be asked to find the what? The area between the red graph and the blue graph. If you didn't know about the lag here, you might be going, what are you talking about? We're talking about these leaves here, the area of these leaves. Notice we have symmetry. And by the way, how many intersection points are there? See, this is where graphing utilities might fail you. If your window looks like this, you might go, oh, it looks like there's one intersection point at the origin. There are 3 intersection points. But when does the 4th power of x equal the 2nd power of x? Well, it's true that the square of 0 is 0 and the 4th power of 0 is 0. But that property is also true for positive 1. The 4th power is equal to the square. And it's also true for negative 1. The 4th power is equal to the square. Okay, so actually the blue and red graphs meet in 3 intersection points. And at these points, that's where the blue graph starts to lag beneath the red graph as you look inside. And they meet again at the origin. So why is that? All right, well, for example, let's take a look at x equals 1/2, a number that's strictly between 0 and 1. The square of 1/2 is 1/2 times 1/2. That's 1/4. But the 4th power of 1/2 is, imagine a discount store that cuts prices in half every week. So cut in half, then cut another half, then cut another half, then cut another half. Those prices get very cheap. You're down to 1/16 of the original price. So if you start sticking in numbers strictly between 0 and 1, the 4th power is beaten by the 2nd power. The 4th power, okay, is less than the 2nd power. I'm sorry, I have it goes this way. The 4th power is less than the 2nd power. I wanted to say that the square of 1/2 is actually greater than the 4th power of 1/2, which might surprise you. The square beats the 4th power. The square beats the 4th power for these kinds of values of x. And at x equals 0 and x equals 1, and at x equals -1, there's a tie, corresponding to these intersection points. But for values like 1/2 or 0.5, the red graph actually beats the blue graph in y coordinate. Here's 1/4, here's 1/16. I'll put 1/2 comma 1/4 is on the red graph, square. I'll go back up here. 1/2 comma 1/16 over there in black. The red graph beats the blue graph for values like 1/2 or -1/2. That might surprise you. Hopefully not too much. All right. So in general, going back here, the x to the 4th graph is steeper out here compared to the red graph, but it's flatter near the origin. What about y equals x to the 6th? How's that compared to both these guys? Y equals x to the 6th. In green, it's steeper out here for values of x far from 0, but for values of x strictly between 0 and 1, maybe excluding 0, right? The green graph is below both the red graph and the blue graph. So again, the y equals x to the 6th graph in green, it's steeper out here, far away from x equals 0, but it's flatter over here, close to the origin. And again, you can talk about areas between various graphs. In calculus, you do that using definite integrals. All right, all of them are even. All of them represent even functions. Next up, how do we deal with y equals x to the 3rd, 5th, 7th, even 1st? Next time. Any questions thus far? I don't know why the CC is failing us today. Any questions thus far? Okay, it should be on the YouTube copy of the class video. Questions? Questions? Hey everyone, this is another one. Did I forget? Another one that's not captioned. All right. Bigger the power, more it's touching the x-axis. Well, it's flatter. So the higher the power for these bowls, the higher the power, the flatter the graph is about the origin. Right. So again, doing the, I should pull up Desmos. Okay, so here's y equals x squared. Here's y equals x to the fourth. Okay, so the graph in green, y equals x to the fourth, it's flatter near the origin, flatter. And it meets with the red graph at the origin. Yeah. But outside of 1 and -1, the green graph's higher and steeper. All right. I'm wondering, I got to look back. I normally do closed caption them. I don't know what's wrong with YouTube. Well,
how do you graph y equals x cubed, or x to the third? Let's point plot. The cube of 0 is 0. Once again, the graph goes to the origin. The cube of 2 is 8. The point 28 lies on the graph. Sorry, 327 might be too ambitious. All right, the cube of 2 is 8, but the cube of -2 is -8. So the point -2, -8 lies on the graph. Remember, for a squaring function or for an even function, if you input opposite values of x, you get the same value. Here, we don't get the same function value, we get opposite function values. Here, the point 28 lies on the graph. I'll do this in green. The point 28 lies on the graph. If that's the case, the point -2, -8 must lie on the graph for an odd function. The cubing function on R is an odd function. It is symmetric about the origin. What does that mean? The graph is symmetric about the origin. So if I take this graph and I rotate it 180 degrees about the origin, I get the same graph. I can almost do this, right? It's like, I can almost do something like that, right? Okay. Also, if you draw a line, you can draw a line through all three of these points. You can draw a straight line through the origin, any point x, y on the graph, and the corresponding point x negative y. Sorry, negative x negative y on the graph. If the point x, y lies on this graph, then the point negative x negative y, or opposite of x opposite of y, will also lie in the graph. So, various ways to think about symmetry about the origin. If you rotate this graph about the origin 180 degrees, you get the same graph. The point xy leads to the point opposite of x opposite of y. You always get those partner points. And you can draw a line through the origin and the 2 points like so. All right. Opposite x values yield opposite function values. Okay. Again, 2 and -2 lead to opposite function values, 8 and -8. Opposite x values lead to opposite function values. F of x and f of opposite of x are always opposites, where x is in the what of the function, the domain. And once again, the domain must be symmetric about 0 to ensure this kind of odd symmetry, so that these partner x values exist. So if xy lies on the graph, so must opposite of x, opposite of y. So officially, when do we have an odd function? A function f is odd. That is, we get that symmetry about the origin for the graph, if and only if this happens. F of opposite x equals the opposite of f of x for all x in the domain of f. So for every x in the domain, that is, every time we get a point on the graph, there's a partner point at the opposing value of x, where the function value is the opposing value. Opposing values of x, the input, yield opposing values for y, the output. Here's a proof. Let f of x be x cubed, where the domain is all reals. For all x in the reals, again, for odd functions and even functions, we want to look at f of opposite of x. And what's the key S word here? Substitution. What happens when we substitute or plug in the opposite of x, or negative x, in for x? Substitution. Substitute the opposite of x for x. So we're cubing, not x, but the opposite of x. Now the cube of the opposite of x is the opposite of the cube of x, right? Basically the cube of -1 is -1. That's the idea. The cube of -1 is -1. And then the cube of x is x cubed. All right. But this now is the opposite of the original rule. F applied to x yields x cubed, right? But f applied to the opposite of x yields the opposite of x cubed, the opposite of f of x. Opposing function values, I'll do this. Opposing function values yield, opposing x values in the domain. Opposing x values in the domain yield opposing function values. If 2 gave us +8, -2 will get us -8 as the function value or y-coordinate. If we replace x with its opposite as the input, we obtain opposite outputs. Now, aside from f of x equals x to the third, what are some other function rules on R that will yield an odd function? Well, consider x to the fifth, x to the seventh, and so forth, even x to the first. We've seen that guy before. How do you graph y equals x? We get this. It's the identity function. The identity function is also an odd function. And in fact, if you have something like x to the -1, x to the -3, these will also give us odd functions, although the implied domain is not R. You have to exclude 0. So why do we call these odd functions? Because any rule, f of x equals x to the n, where n is an odd integer, that will give us an odd function. Here, the domain is all reals for these over here. The domain must be symmetric about 0. All right. Now, how do these graphs compare? It's kind of similar to what we saw before. Okay, here's y equals x for that matter. Here's y equals x. That's odd. Here's y equals x to the third. I think of these guys as snakes. Y equals x is like a dead straight snake. Y equals x cubed is a curvy, rising, tall, proud snake. Y equals x to the fifth. Y equals x to the fifth in green. That's also a tall, proud, rising snake. All right. Notice, away from x equals 0, the green graph is steeper than the blue or the red graph. The green graph is steeper. But if you zoom in close to x equals 0, for values of x like 1/2, for example, or 1/4, or 0.1, or 0.9, notice that the green graph, y equals x to the fifth, is actually very flat compared to the blue and red graphs. So again, if you consider y equals x to a positive odd integer, right, then we get these snakes. They're steeper and steeper away from x equals 0, but the graphs get flatter and flatter as you get closer to the origin. They all go through the origin. And these all represent odd functions, where domain is R. Are there functions that are both even and odd? Yes. The 0 function on R is both even and odd. y equals 0. Look at that graph. Is it symmetric about the y-axis? Yes, the graph is even. Is it symmetric about the origin? If you take this thing and you rotate it 180 degrees about the origin, do you get the same graph? Yes, you do. f of x equals 0 on R, the set of all real numbers as a domain, that's both even and odd. Any zero function where the domain is symmetric about 0 will be both even and odd. Although many functions are neither even nor odd. If I give you something like f of x equals x to the third plus x to the second, what is that? Is that even? Is that odd? No, it's neither. It's neither even nor odd. Y equals x to the third. Hey, that's our nice snake. But then try to add x squared. That's messed up. We lose both even and odd symmetries. That's messed up. It's neither even nor odd. That's typically the case when you add an odd and an even function that aren't 0. Next up, more powers of x. By the way, at this point, you should be able to graph anything of the form y equals x to a positive integer.
Let me, wait, something happened here.
What's the graph of y equals x to the first? It's a line, dead snake, dead straight snake. How about y equals x to the second? That's a bull. In fact, it's a parabola. Y equals x to the third. That's a rising snake, that's curvier. Y equals x to the fourth. That's a bull, but not technically a parabola. How about y equals x to the 99th? That's a snake, steep on the outside, flat on the inside. X to the 100th. That's a bull, again, steep on the outside, flat on the inside. Next up, y equals x to 0.
All right, any questions? Got some problems with YouTube today. All right. Can we get some captioning here? Again? Oh, well.
Hi, everyone.
All right.
So how do you graph y equals x to the 0? Well, what is 2 to the 0? What's 3 to the 0? What's negative pi all to the 0? All of these are equal to 1. Remember the rules of exponents? These are all equal to 1. However, 0 to the 0 is kind of weird. Some books say that 0 to the 0 is undefined. In calculus, you talk about the 0 to the 0 indeterminate limit form, where the base and the exponent approach 0. But now, 0 to the 0 is sometimes defined as 1, especially if you're dealing with polynomial theory. So for example, if I'm talking about polynomial theory, I might refer to 1 as 1x to the 0, where x to the 0 is simply 1, even in the case where x is 0. So if I'm talking about polynomials, like in chapter 2 especially, then I may adopt this convention. So it kind of depends. If 0, okay, well, first of all, how do you graph y equals 1? You agreed that this is still basically y equals 1. How do you graph y equals 1? It's going to be a horizontal line. Although, if you say that 0 to the 0 is undefined, then you have a hole at 0, 1. Because if you're saying that 0 is not in the domain of x here, then you're not allowed to have a point there. So we have a hole. If you define 0 to the 0 to be 1, however, then you can spackle in that hole and just get your usual line, y equals 1, if you define 0 to the 0 to be 1. Desmos, for example, when you graph y equals x to the 0, it basically graphs y equals 1, and it appears to define 0 to the 0 to be 1 on Desmos. Of course, on Desmos, you often deal with polynomials. In either case, though, whether there's a hole at 0, 1 or not, we have symmetry about the y-axis. And therefore, in either case, the zero function, the x to the zero function is an even function in either case. It's basically a constant function. Remember, constant functions are even. Constant functions are even. That was true for y equals 1. That was true for y equals 3, all the way up here. Okay, this was an even function. All constant functions are even. All constant functions are even. Whether you have f of x equals 1, 2, 3, -3, even 0. In fact, that represents both an even and odd function. All constant functions are even. That might sound strange because if I say f of x equals 3, you might be saying, wait a minute, isn't 3 an odd number? Yes, 3 is an odd integer, but we don't care. We don't distinguish between even and odd integers. 3 is a constant. All constant functions are even functions. This represents an even function. I don't care that 3 is an odd integer. All constant functions are even functions. I know that's confusing. Next up, what happens if we have y equals x to a negative integer? How do you graph those things? That's next.
All right. Any questions thus far? Any questions thus far? I'm curious. Why is the CC off today? All right. Any questions? Okay.
Next time.
Uh,
Hey everyone, how do you graph f of x equals x to the -1? What's another way of writing x to the -1? 1 over x. So what does this function do to its input or argument x? It takes its what? It takes its reciprocal. How do you graph the reciprocal function? What's the graph of y equals 1 over x? Okay. By the way, a reciprocal is also called a multiplicative inverse. When you multiply these together, you get 1, the multiplicative identity. But how do you graph y equals 1 over x? Let's do some point plotting. Now, first of all, what's the domain of this function? We should ask that early on. The domain is the set of all real numbers except what? Except 0. So you plug in 0, it's undefined. But we can plug in 1. The reciprocal of 1 is 1. The reciprocal of 10 is 1/10. The reciprocal of 100 is 1/100th. As x approaches infinity, if x goes to 1,000, 1,000,000, 1,000,000,000, these function values, these reciprocal values, they go to 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. They seem to be approaching 0 from above. That's why I have 0 plus here. So based on this point plotting, you might guess that this is a piece of the graph where the point 1, 1 is on the graph, and as x approaches infinity, the y-coordinates, the function values, approach 0 from above. Notice that the x-axis is a line that the graph approaches in the long run. We call the x-axis an HA, or I do. What does HA stand for? It's a horizontal asymptote. In general, an asymptote is a line that a curve or graph approaches in either a long run or explosive sense. Here we're looking at things in a long run sense. The distance between the graph and the line approaches 0. We usually indicate asymptotes as dashed lines, although sometimes if the x-axis is an HA, or if the y-axis is a VA, a vertical asymptote, some books don't bother. Okay, now, what about values of x strictly between 0 and 1? We know we have a problem. When x equals 0, we won't get any points here. But what's happening as we travel from x equals 1 backwards towards x equals 0? What happens as x approaches 0 from the right? Now we're thinking calculus. It's like we're taking the limit of the function as x approaches 0 from the right. A table. going from right to left. The reciprocal of 1 is 1 again. That's why 1, 1 is a point on the graph. I'm just reiterating that. But now the reciprocal of 1/10 is 10. The reciprocal of 1/100th is 100. The reciprocal of 1 over a million is a million. So it appears that as x approaches 0 from the right, from greater numbers, the function values, the reciprocals, will be approaching infinity. In calculus, you might write something like this. 1 over x approaches infinity as x approaches 0 from the right, or from greater numbers. So then, you should agree that as we move from x equals 1 towards x equals 0 from the right, that the y-coordinates are approaching infinity. And then you might agree that the graph in quadrant 1 looks like this hook here. But it's an infinitely long hook. Now in calculus, you are going to define asymptotes in terms of limits. So again, the y-axis is a vertical asymptote, or VA for the graph, because the function values themselves are approaching infinity as x approaches a number from the right or the left. Now, what happens if you replace x with its opposite? You get 1 over the opposite of x, or the opposite of 1 over x. This is the opposite of f of x. F of x is 1 over x. Right. The domain of the function is all real values except 0. That's set difference notation. So the domain is symmetric about 0. What am I getting at? This reciprocal function is what kind of function? It is odd, which means that the graph is symmetric about the what? It's symmetric about the origin, which means that we have this graph in quadrants 1 and what other quadrant? Quadrant 3, which makes sense because, for example, the reciprocal of 1 is positive 1, but the reciprocal of negative 1 is negative 1. So it makes sense that if xy is a point here, then opposite of x, opposite of y will be a point here. Reciprocals of negative numbers are themselves negative. And 0 has no real reciprocal. That's why we don't have any points on the y-axis. We do, however, have an HA at the x-axis and a VA at the y-axis. All right, that's the graph. You go to Desmos, y equals 1 over x. And if you remember your Algebra 2 class, this is a conic section. Which conic section is it? It's not a circle. It's not an ellipse. It's not a parabola. It's a hyperbola with the axes at the coordinate axes. Here are the axes. An HA at the x-axis, y equals 0, and a VA at the y-axis, given by x equals 0. These should be dashed though. All right. Now this is called a hyperbola. What other graphs will look similar to this guy here? Well, how about y equals x to the negative 3, for example? How can you rewrite x to the negative 3? As 1 over x cubed. And so forth. Y equals x to the negative 5th, or 1 over x to the 5th. All these guys are going to have these quadrant 1 and quadrant 3 type graphs with these as asymptotes. Okay, but they're not called hyperbolas. Okay, y equals 1 over x gives a hyperbola. These are not technically hyperbolas over here, but their graphs are somewhat similar. Y equals 1 over x cubed, for example, in red, that's flatter as we approach the x-axis out here, but it's steeper as we approach the y-axis. The values climb up faster. Don't worry about that. Next up, how do you graph y equals x to the negative 2. Oh, by the way, on Desmos, let's do a comparison. Here's y equals 1 over x cubed. Okay, so that's in red versus the green graph. Again, the red graph approaches the x-axis more quickly, but not the y-axis, because these values are steeper over here.
Wait, questions before we go on. Any questions? Any questions? Any aspects that are tricky so far? All right.
Hi, everyone. How do you graph y equals x to the negative 2? How can you rewrite x to the negative 2? It's 1 over x squared. Now, if f of x is x to the negative 2, consider f of opposite of x. What happens if you replace x with its opposite? Well, the square doesn't care about the negative 1 factor in here. We just end up with 1 over x squared, or f of x itself. That's true all throughout the domain, which is going to be this over here, all reals except for 0. Same domain here. Symmetric about 0. What kind of function is this? It is even, which means that the graph is symmetric about the y-axis. Y equals x squared, we know, is symmetric about the y-axis. What about this guy? Now here's y equals 1 over x. This was odd, remember? Symmetric about the origin, 0, 0. But now, what about y equals 1 over x squared? How would that graph be different? Yeah, in quadrant 1, it'll look a bit different. But how will this graph be different? It's going to be in quadrants 1 and what? Not 3, quadrant 2. If you said quadrant 4, be careful because you probably don't have a function then. If you have a quadrant 4 piece, right? Okay, y equals 1 over x squared. Let's choose a better color. How about blue? Here we go. In blue, right? Y equals 1 over x squared. I call this a volcano graph. Quadrants 1 and 2. So the piece in quadrant 1 looks kind of similar to the piece for the green graph, y equals 1 over x. But the key difference is, okay, for the volcano, the other piece is in quadrant 2, not quadrant 3. We have an even function, not an odd function. We have symmetry now about the y-axis. You can do some point plotting, but that's the basic idea. Okay, here's y equals 1 over x squared. And then for other guys, y equals 1 over x to the 4th, or 1 over x to the 6th. That is x to the negative 4, x to the negative 6, and so forth. All right, you'll have similar graphs, quadrants 1 and 2. So if I have y equals 1 over x to the 4th, y equals 1 over x to the 6th. All right, flatter out here, steeper in here. All right, similar. All right, at this point, you should be able. Oh, and by the way, we have the same vertical. We have the same asymptotes. The x-axis is an HA. The y-axis is still a BA. Now, at this point, you should be able to graph anything of the form y equals x to an integer. Next, what about y equals x to some other rational exponents?
Okay, any questions? Any questions? We'll probably end the videos around 8:10 to 8:15 or so. Yeah. Any questions?
Hi, everyone. How do you graph y equals x to the 1/2? Well, what is that? That's the principal square root of x. And we've seen that before. It's this hook, and you must indicate the endpoint at the origin. This hook goes through quadrant 1. It gets flatter and flatter, but there's no HA. The square root of a million, the square root of a billion, the function values shoot off to infinity. But now, is the square root function an even function? Is the square root function an even function? Is it symmetric about the y-axis, the graph? And the answer is No. What's the problem? The domain of the function, what is the domain of this function? It's the set of non-negative reals. It is not symmetric about 0. We do not have symmetry about 0. For example, 1 here is in the domain, but its partner opposite value, -1, is not in the domain. So the square root function, although it sounds like it, it is not an even function. Now, the square root graph looks like the graphs for the 4th root of x, the 6th root of x, and so forth. Even for something like x to the 3/4 or x to the 5/8, where the exponent is proper, odd integer over even integer, you'll have similar graphs as these. Domain is the non-negative reals. Now, what about the cube root function? Y equals x to the what? X to the 1/3. That's the cube root function. What's the domain of this? What's the domain? It's not just the non-negative reals. The domain is going to be all reals, because you are allowed to take the square root of a negative number. You're allowed to take the square root of a negative, or sorry, you're allowed to take the cube root of a negative number, the 5th root of a negative number as well, right? So the graph kind of looks like the square root graph in quadrant 1, and you get the origin, but it's an odd function. It is an odd function. Symmetry about the origin, the cube root of -1, for example, is -1. So the cube root function, again, I'm telling you how to think. You like cube roots. You like the odd roots. Domain is all reals. We get this S-shaped curve. It's an S curve, an S graph, and these functions are odd. So is the 5th root of x, so is the 7th root of x, even something like x to the 3/5 or x to the 5/9, where the exponent is proper, odd over odd. Next, we're going to see something strange. X to the 2/3 next.
Any questions? Finally, some closed captioning. Hey, wait, what happened?
Hi,
Oh, I
Ron.
know what happened. Whoops.
How do you graph?
Okay, any questions? Any questions? Finally, a CC video. Any questions? All right.
Hi, everyone. How do you graph y equals x to the 2/3? Well, how can you write that in radical form? How can you write x to the 2/3 in radical form? You could write it as the cube root of x squared. What is the domain of this function? Well, you can take the square of any real number and get a real result. You can take the cube root of any real number. So domain is all reals. Is it even or odd? Well, if we substitute x with its opposite, the square doesn't care about this -1 factor. We end up with the same result. So it's even. Domain is all reals, and it's an even function. What does this look like? In quadrant 1, we get a hook, kind of like the square root or cube root, but it's an even function. Symmetry about the y-axis. This is like a bird beak, a funnel, or tornado. And this point at the origin is called a cusp. This is the nicest graph where we get a cusp in calculus, where we have continuity, and we have infinite steepness from both sides, but in opposite ways. A cusp. Many graphing calculators have a hard time doing this. Desmos can do it. Y equals x to the 2/3. Okay. In general, if you have x to a proper fraction, even over odd, you get a bird beak like the above, like x to the 2/5 or x to the 4/7. What about absolute value? Now, actually, this is an algebraic function because you can think of the absolute value of x as the square root of x squared. But here's the piecewise definition. We have basically y equals x if x is non-negative, and y equals the opposite of x if x is negative. How do you graph these? Well, it's a piecewise graph. You get the piece of y equals x here, so you get a piece of this line here, and you get a piece of y equals the opposite of x with slope -1. You get a piece of these two lines, and they come together at the origin. Here's y equals x over here. Here's y equals the opposite of x over here. Even, odd, or neither. Symmetry about the y-axis, it's even. Also remember, the absolute value of opposites are equal. Domain is all reals. That's the V-graph, the V-graph. And this is called a corner, not a cusp, because you don't get infinite steepness. Upper semicircles. Remember when you took this equation, solved for y, took the non-negative root, y equals root 9 minus x squared, remember? Y equals square root of 9 minus x squared. That was the upper half of a circle of radius 3, centered at the origin. In general, if you have y equals the square root of a squared minus x squared, where a is positive, you get an upper semicircle of radius a, the upper half of a circle centered at the origin. Remember this form. Look over the gallery of graphs. It's a summary of what we just did. Be able to graph all these basic functions. And then you want to have to point plot all over the place. We can fall back on these. In section 1.4, we're going to manipulate and transform these.
All right, so that's the videos. Actually, let me, I'll pause the recording here. That's all I have to say for today. The rest of the class is yours, all right? So I'm going to go to chat now. All right. Okay, so yeah, now before I go to particular questions, I'd like to ask the class, do you have any questions about how you submit your homework? I sent an email today recommending that you put page numbers on your homework. That helps me. That really helps me if you put page numbers, because if your stuff's out of order, it really helps for me to know what the order the pages are in. And also, I recommend you CC yourself, check what you sent me so that you can check to make sure that you give me something good, right? Good order and all that. So again, any general questions about submissions of the homework, right? Show your work where appropriate. It's due tomorrow, not tonight, tomorrow, midnight, 11:59 p.m., tomorrow, all right? After that's late. Okay, any general questions? Any general questions? Okay, so I'm going to proceed recording. If at some point the class wants me to stop recording, I will obey your wishes, but I see no point in stopping it right now. So I'll stop it if you tell me to, all right? Okay, so I'm gonna go in order in the chat. Although if for some reason you have to talk to me, but I'll follow the chat here. Oh, now let me see. You know, some of these I did in the Tuesday YouTube video, in which case I might refer you to that. Okay, so let me check what happened here. Because then right now, you might be able to check my YouTube channel. Wait, was it, yeah, 0.9, okay. Ah, okay, so here's the deal. I'm glad Nick brought up F. I believe F was the only one I didn't do on Tuesday. Among the three monsters here, I believe I did D and E in the Tuesday video. Isn't that correct? Yeah, I did D for the YouTube video from Tuesday, and also E. F is new. So here's the plan. I'd like to do F now because that was not in the Tuesday YouTube video, okay? And then I'll address other questions. As time permits, I can go back to D and E. But for those of you who really want D and E, right now, you're welcome to go to the YouTube video from Tuesday. It's the last one I posted from the Tuesday session, and I have the solutions for D and E right now on the YouTube video. So I'll do G. G I didn't do. Right. So F and G I'll do now. Okay. Yeah. All right. So that's the plan. I'll start with 0.9 F and G, and then I'll take any other questions. All right. Again, if you want D&E, you might want to check my YouTube video right now. You're totally welcome to do that. Whew. All right, so let's do F, right? That was the only major monster I did not do Tuesday. So, okay. We're doing 0.9, 1F, 1F. All right. Okay, now to save time, I'm going to go ahead and apply the substitution right now. Okay, you should state the substitution. Let U equal, what's the thing that's being copied all over the place? Is that base, let's see, 2x cubed plus 5. I'm recording, aren't I? Yeah, I'm still recording, right. Yes, yeah, the plan is for me to post the recording. However, bear in mind that, you know, as we've seen, there can be technical glitches. Also, if the students wish by consensus for me to stop the recording at any time, I'll stop the recording. But the plan is for me to record and post. I don't see real objections to that. All right. And I should post by tomorrow, early tomorrow morning. All right. So let U equal 2x cubed plus 5. Yeah, that's one of the reasons why I want the homework due tomorrow, not tonight. All right. Let U equal 2x cubed plus 5. Okay. So I'll call this star. All right. Because I'm lazy. I don't want to recopy the whole thing. Right. Okay. Star. Okay. That given thing equals. Okay. So I'm going to apply the substitution. We have U to the 2/3. In fact, if you don't mind, I'm going to put the 8x in front. It is conventional for us to put the nice polynomial pieces in front. All right. So the 8x I'll put first. This is going to be U to the 2/3. All right. So the upper left becomes 8x U to the 2/3. If you want to put the x, if you want to do U to the 2/3 times 8x, that's fine. I'm just cleaning it up now. All right. Okay. Minus, and then remember, don't try to blend these two terms up here. Okay. Like the 2/3 and the 6, don't try to move that over. All right. Unless you're factoring. Let's just simplify right now. Okay. We have a negative coefficient on the upper right piece, the term up here on the top. All right. What goes with it? What number? All right. I see here a 2/3. I see here a 6. Remember, multiplication is associative and commutative. I can multiply these factors in any order. All right. I'm going to multiply the 2/3 and the 6. 2/3 times 6/1. You can do some cross canceling. 3 goes into 3 once. 3 goes into 6 twice. We get 4. So the coefficient in the upper right is a negative 4. All right. So negative 2/3 times 6, we got a negative 4. All right. And then I have this polynomial piece, the parenthesis 4x squared minus 3. And then the more general algebraic piece, U to the negative 1/3. All right, and this all goes over. Now this is the U guy again. It's going to be U to the 2/3, and that's all squared. So I've done a lot of cleaning up here, but a lot of students have questions about the cleanup, especially the way I got the negative 4 there. Any questions about that? Any questions about how I got that negative 4?
Professor, I have a question.
Go ahead.
Don't we need to write x squared after the 4? Because you multiply.
Oh, thank you. Yeah, did I forget the x squared here? Thank you. Thank you. All these pieces. All right. X squared over here. Thank you. Yeah, I outright forgot that. X squared. Okay. But again, the coefficient, the numerical coefficient will be negative 4, right? We have negative 2/3 times 6. Yeah, my circle is too big here. Right. There's an x squared there I forgot. Thank you. All right. The x squared, that's also polynomial. Then the 4 squared minus 3 in parenthesis. All right. And then U to the negative 1/3. Later on in the course, when I go to my old videos, I'll have thinner marks. There'll be pros and cons of that. All right. Anyway, any more questions or corrections? Okay. By all means, if I made a mistake, please let me know. Any questions? All right. And you all agree with the -4. You all agree with the -4, right? Okay, let's move on. All right. What shall we do here? All right. Equals. On the bottom, we can take care of this right now. On the bottom, we're squaring u to the 2/3. Okay? When you raise a power to a power exponent, what do you do to the exponents? All right? You multiply. Multiply. When you raise a power to a power or exponent, you multiply. So 2/3 times 2/1, I'm not kidding. All right? 2/3, this is side work, right? I encourage side work. And we get 4/3. So the new exponent on the bottom is 4/3. All right. All right. That's new exponent on the bottom. On the top, you know, most students prefer that I factor out that power of u. If you prefer the compound fraction method, we could do that at some point. But I'll go ahead and use the factoring method up there. All right. And I think I'll go ahead and be brave. I'll go ahead and factor out the entire GCF. Okay, although you may not have to do the whole thing, all right? So for example, I see an 8 and a 4 or -4. I'll go ahead and factor out a 4. I'll do this in blue. All right. Now, it turns out that since I don't think 4 is going to be a factor on the bottom, I don't think I have to do that, but let's go ahead and factor out the entire GCF, all right? So we have the 8, we have the 4 or -4, we factor out the 4. Okay, next. We have the x, and we have the x squared. Which piece do we factor out? The x or the x squared? We factor out the power of x with the least exponent. That's x to the first. That's the plain x. Although, as it turns out, we may not have to factor it out because I don't think x is going to be a factor on the bottom anyway. All right, next. Now, this is what you really need. This is the really key part here. I'll do this in red. I know you have to do this if you're going to use factoring. U to the what? We have u to the 2/3 here. You have u to the -1/3 here. Okay, you're going to factor out u to the, factor out u to the -1/3, right? And that's the key thing, okay? I don't think you have to factor out the 4 or the x, but you have to factor out the u to the -1/3 if you're going to use the factoring method. Again, you could also rewrite this as a compound fraction. All right, very good. The rest, let's go to black. All right, go here, bracket. When we factor, we do a D word. When you factor, you do a D word. We're going to see this in chapter 2. When you factor, you divide. Good, you divide. All right, I'm going to divide this thing, the 8x u to the 2/3, by this thing over here. I'll go piece by piece. 8 divided by 4 is 2. X divided by x is 1. Don't worry about that. By the way, don't worry about domain, all right? For here. This is the hard part, okay? U to the 2/3, we start there. When we factor, we divide. When we divide powers of u, what do we do with the exponents? When we divide powers of u, what do we do with the exponents? We subtract them. 2/3, take away the -1/3. I normally don't like to micromanage, but I'll make an exception here. What's 2/3 plus 1/3? What's 2/3 plus 1/3? That is 1. So even though I normally don't like students doing this here, make that a 1. That may be an improvement. Okay. But like I said, don't do too much here. Like, don't do your side work in the actual work. But here I'll make an exception. All right. We get 2u to the first. That's very promising. All right. So we're done with factoring this out of this, right? Here's that quotient we get, okay? Big old minus sign. Next up, upper right corner here. 4 divided by 4 is 1. We can ignore that. X squared divided by x, that's going to be plain old x. X to the second divided by X to the first is X to the first. Ah, good. U to the negative 1/3 divided by himself is basically 1. Don't worry about domain. End bracket. Wow, that was a lot easier. Okay. Not a rhetorical question. Did I make any mistakes? That's not rhetorical. Did I make any mistakes? I'm thrilled when I get my own questions. All right. Equals. All right, I'll clean this up. So we have 4x. Where does the -3? Oh, that's in the that was substituted. Did I forget that? Yeah, I forgot that, didn't I? Wait. Yeah, I forgot that. Thank you for just forgetting things. All right. Okay, so 4 divided by 4 was 1. X squared divided by x is x. And then this thing, yeah, I still need the 4 squared minus 3, right? I skipped it. I'm doing what a lot of students do. I'm missing pieces. Yeah, that's often a common error. We're just skipping over pieces. And then the power of u divided by himself. Yeah, thank you. All right. So now we're good, right? Okay. So let's clean this up. 4xu to the, I think I'll go back to blue. I'll go back to blue. I'm going to extend the bar a bit. All right. So we have 4x u to the negative 1/3. Okay. Let's do some black. Bracket 2. U to the first is just u. Plain old 2u. Okay. Minus. Okay, folks, I'm going to announce this right now. I am going to make a mistake on purpose. All right. Let's see. X times 4x squared is 4x cubed. X times -3 is -3x. I made a mistake. That's correct. So one of two things. Either make that plus or group this. I'll actually put that in red. I'll put that in red. Okay. So when you subtract this product, be careful, because when you expand the product, you get 2 terms. But when you subtract off something with 2 or more terms, you better group. And you know what? A lot of students make a mistake here. I mean, aside from skipping things the way I did, right? Mechanically, the things that people miss the most, grouping symbols and signs. You have no idea how important these things are. Or you can change that to a plus immediately, right? So if you want to think of it as multiplying in -1x, then you would have caught that. You'd make that a plus sign immediately, right? Without the grouping symbol. So without the grouping symbols, you put a plus sign, right? Over u to the 4/3. Okay, again, not rhetorically. Did I make any mistakes? Okay, are we good? All right. Equals. We're pretty close, actually. All right. Okay, here's what I'm going to do next. In fact, I might not want to do this just yet. This is really a big part of the problem. We're dividing u to the -1/3 by u to the 4/3. Can we do this kind of division? Yes, we can, because look up there. The top there is factored. 4 times x times this power of u times this ugly thing in brackets. I know the top is ugly, but it is one term in factored form. U to the -1/3 is a factor of the entire top. U to the 4/3 is a factor of, it is the entire bottom. So we can divide, okay? What do we get? All right, u to the -1/3. This is side work. Divided by u to the 4/3. When you divide powers of u, what do you do to the exponents? When you divide powers of u, thank you, you subtract. In order, -1/3 minus 4/3. Don't switch because you feel like it. It's the top exponent minus the bottom. -1/3 minus 4/3. What is that? That's u to the what? -5/3. You all agree? I divide this guy in blue, divided by this guy in green. All right. So that's u to the -5/3. What's another way of writing that? Because we don't like negative exponents in the end. What's another way of writing that? Yes. 1 over u to the +5/3. It's that jumping rule. Yeah. Well, 1 over u to the 5/3. Don't forget the, 1 over u to the 5/3. All right. So bottom line, if I divide u to the -1/3 by u to the 4/3, what's left? What do I put and where? What do I put and where? This is all side work. You end up with u to the 5/3 in the bottom. Because the idea is that you're taking these other guys, you're multiplying by this blue guy over this green guy. U to the -1/3 over u to the 4/3. When you multiply with this fraction, you're multiplying by this nice fraction, 1 over u to the 5/3. That has the effect of putting u to the 5/3 on the bottom. Okay, now I have 4 squared minus 3 here. I'm multiplying in the x, right? So 4x squared minus 3 is here. And then I multiplied in an x and then grouped. Right now I'm focusing on this division, but does anyone see an error here? Okay. Again, Pei Hong, I multiplied in the x, so that's why it looks like that. Yeah, but I know it's hard to follow. I don't blame you. Yeah. All right. Okay, we're good so far. All right. Well, not yet. That's okay. That's okay. I haven't done that yet. Yeah. If you want to do that now, that's fine. But I'm focusing on this issue here. That's the thing that really concerned me. Oh, okay. Now here's the deal. On here, right? It's minus x times the quantity 4x squared minus 3. Now, if I leave that as a minus sign, when I work out the product, I can work it straight. X times 4x squared is 4x cubed. X times -3 is -3x. And that's okay if I put the grouping symbols. Okay, so I am putting in the grouping symbols. As it stands, with the red parentheses, this is correct. This is correct. Okay? All right, but I will change the sign later. When I remove the parentheses, I will change the sign. Right, James is correct. I only distributed the x, not the -1x. If you wish to, you can. I would not take off points. I'll believe you, right? You don't have to show that additional step. If you want to multiply a -1x, change the sign directly, that's fine. But I would advise that you be careful, though, right? I think this is actually safer, but it's up to you. Whatever works. Okay, but thank you for calling me on this, because it's good that we clarify this, because I'm sure many people were wondering. But this is a real crux of it. Okay, this goes beyond a sign issue. All right. You all agree we have u to the 5/3 on the bottom. That's where I am. We have u to the 5/3 on the bottom. Okay. On the top, we have the 4. We have the x. We've taken care of this guy, right? The u to the -1/3. We've taken care of that issue. We can skip him. All right. Bracket 2u, and then let's do what everyone is suggesting, which is I'm going to distribute the -1, and I get -4x cubed. What? And this is what everyone's concerned about, right? What? That is a plus sign. Right. 3x, though. 3x. Right. There's still the x there. All right. And as far as the u's go, we're done with the u phase at this point. The next step is that I'm gonna sub back. So this is a good place to pause. I got to go to another whiteboard anyway, but good place to pause. Any questions so far? And thankfully, this is being recorded too. I might want to keep the recording for later. All right, any questions so far? We're almost done. Sub back. Okay. It was this thing here. Right? So we're going to sub back. Oh. All right. So 4x bracket 2 times, what was u? U was 2x cubed plus 5. Okay, you need the parentheses here. You often do. All right, minus the 4x cubed. That's a minus sign. Yeah, make your minus signs big and long there, because sometimes minus signs look like times dots sometimes. Mine do too sometimes. Gotta watch out. Minus 4x cubed plus 3x, right? Minus 4x cubed plus the 3x. Okay, and I'll conscientiously extend my bar there, right? All over u, which is what the 2x cubed plus 5. The 5/3. All right, we're very close. Okay, on the top, we have 4x. There's no point in multiplying it back in. 4x times a quantity. We distribute, all right? The classic distributive property. The 2 goes into here and into here, but nothing to do with these guys, right? So 2 times 2x cubed is 4x cubed. 2 times 5 is 10. I can do that. All right. Oh, and something really great happens. This looks familiar. Yeah. Why am I so happy? Oops. Minus 4x cubed. This won't always happen, but it happens here. Because what great thing happens? This doesn't always happen, but it happens here. All right, what happens on top? Okay. One advantage of the screen over markers. I don't have to worry about corrupting my markers. Yoink, yoink. 4x cubed minus 4x cubed is 0. That sounds familiar. All right. Because I've done this problem before. Even though I still mess it up sometimes. All right. All right. Equals, I think we're there, right? 4x. I don't care if you put parentheses or brackets. Doesn't matter at this point. What? 10 plus 3x. Over, yeah. Is that correct? Well. All right. Let me... Okay, I think this is correct, right? So 4x times the quantity 10 plus 3x, or 3x plus 10. I don't care what order you put them in. All over the 5/3 power of 2x cubed plus 5. Wow. So I'm thankful for your help. I needed some help from a couple of you sometimes, but we got there. All right. Okay, now this is a heck of a question. Any questions? That sounds almost sarcastic, but any questions? Any questions? I should probably number these, huh? Okay, I'll pause. I'll give you about 20 seconds. Now, again, this is going to be on YouTube. That's the plan. Okay, unless there's a glitch. All right, I'll give you about 20 seconds to look this over. By the way, I propose a break. I think people need a break after this monster. That's the plan. Yeah, that is the plan. Assuming that students are okay with it, I don't see why students would object. But I think that's the plan. That's the plan. Should be good. Good night. So are you folks cool? In fact, let's do this. If you want to, I'll keep this up. Let's take a 10-minute break. If you want to look at this for 10 minutes, that's cool. Let's take a 10-minute break, okay? And then we'll reconvene at 8:48. All right. I'll give you plenty of time to look at this. And record. I'm gonna put this. Remind me if I forget, please, because Nick just asked about that. Record in 64-point font. Record. All right. So I'll see it like 8:48. All right. Okay, I am recording. All right. Okay. Okay. So yeah, I have a question about rationalizing. Now, before I go on, I'll save these little whiteboards here. Any questions about this monster before we, bury it, put it to bed? Oh, am I talking too loudly? Wait, is my volume too high? Oh, okay. Oh yeah. No, Dylan has a sense of humor. That's right. Okay. All right. Okay, but I am recording, so yell at me if I'm not recording, because people be mad. Students will yell at me if I'm not recording. All right, I am recording. I just hope it'll catch, right? All right. So are we good? Can we move on? No. Well, I should frame it this way. Are there any questions about this? Any questions about this? Obviously, there's a lot of potential for confusion here. I needed your help to not skip things. Are there any questions about this? Okay. All right. Okay, so go ahead. I've saved this. By the way, if you have a MacBook like me, what I'm doing for these is I'm taking a screenshot of a blank text screen. But the thing is, I got to convert to PDF because that's the only way that you can save the writing. If you save it as like a PNG, it won't save. So that's a tip for those of you who are using Preview and Markup Toolbar. Or am I the only one? All right. Yeah, I know there's a question. Actually, James had a question way up there too. Yeah. So, okay, so James had a question about rationalizing, and then Danny had a question. Oh, wait, Danny had a question about this one. Oh, shoot. But I've saved it though. Hold on a second. Hold on a second. Okay, good. All right. Yeah. Good thing I have these things here. All right. So Danny had a question. How do we start factoring the top of the fraction again? All right. Oh yeah, I was being really ambitious because I actually did try to factor out the GCF. In class, I often wouldn't do that. But to be honest, because my whiteboards are kind of tight here, I kind of want to combine steps. Because I might have started by factoring out the 4 and then the x. But here, I was ambitious. I factored out the entire GCF. So I'll reiterate this. Whoops. All right, so let's see here. Orange. I claim that this is the GCF. Okay, 4xu to the negative 1/3. Okay, I claim that's the GCF. Although, as it turns out, the 4 and the x, because they're not factors of the bottom, it turns out that that's not so necessary. But still, as a matter of practice, people are encouraged to factor out the GCF, maybe in pieces, okay? So I'll explain this first step here. Okay, All right. Okay, so let's see. So Daniel, is that your question about the GCF? Yeah. Okay. So and let me know if you'd like me to continue further. All right. So piece by piece. Now remember, we have two terms up on top. Uh, in fact, I'll put them both in black. We have 8x u to the 2/3. That's the first term on top. All right. And then we have this big, ugly term up here with many factors. All right. I want to find the common pieces from both. We can ignore the sign here. So 8 and 4. The GCD, the greatest common divisor, is 4, right? That's the biggest thing that goes into both nicely. 8 and 4, we get 4. X versus x squared, we factor out the we factor out the power of x with the least exponent. That's the x. In basic algebra, if you had x plus x squared, it would be your sense to factor out the x, right? So we factor out the x. Now this is the hard part. We have u to the 2/3, and we have u to the negative 1/3. This is the hard part. We factor out which power of u? Again, we factor out the power of u with the least exponent. That's the negative 1/3. Remember, any negative number is less than any positive number. So u to the negative 1/3. So that explains the GCF. All right. Are there any questions about the GCF? Because when we factor, we divide. My next step is the division. All right. So we factored out the GCF. The next step is to divide to get the stuff in brackets. All right. Or parentheses. I don't care what type of grouping symbols you use, but put grouping symbols. All right. So I have the brackets here. Now, my first term I've circled up here in the top. I'm going to divide that by the GCF. 8 divided by 4 is 2. X divided by x is 1. The x disappears here. This is the hard part. U to the 2/3 divided by u to the negative 1/3. We're dividing powers of u. When we divide powers of u, we subtract the exponents. But fortunately, when we do that, the result is 1, which we can then delete, right? We don't have to write down the 1. So this divided by this is just 2u, all right? And then this, even I messed this up. Okay, be careful. The minus sign carries over, right? Basically, negative 4 divided by 4 is negative 1. The minus sign carries over. X squared divided by x is x. Out of wishful thinking, I forgot about this piece, okay? But a student was good enough to remind me. And then the group 4x squared minus 3. U to the negative 1/3 divided by itself is 1. Don't worry about domain or hidden restrictions or any of that, okay? The u guys die over here. And that goes over here. I use the fact that when I raise a power to a power, or exponent, I multiply the exponents. That's u to the 4/3. So that's a huge step, okay, but worth reiterating. I'm sure many students had this question. All right. You're welcome. Are there any other questions here? Because there's a lot of good algebra here. We are not wasting our time. Or I don't think you are. Are there any other questions about? Now, thankfully, I say this for Dania. I'm saving these. I'm not erasing them. They're in PDF form. All right. Any questions about the monster? Any other questions? I'll keep these saved. All right. Save. All right. James had a question about rationalizing way up here. James Harris. Okay, request for example and methodology on rationalizing numerators and denominators for section 0.9. Okay, or we could do a homework problem. Did you want to go over the homework problem, or did you want to just do like just a general thing, James? Or basically, do you want a recap of rationalizing? Or what do you think? A general example? Okay, so let's talk about some principles. Okay. And in fact, you know, whether it's the numerator or denominator, it doesn't really matter, right? It depends on the form that the radical expression takes. So let's, where am I? Okay, 39, all right. Okay. Okay, so in the beginning, let's do a very simple example. 1 over the square root of 2, the most elementary example, right? I don't like the fact that the denominator is irrational, but I can rationalize it by multiplying by 1. Okay, you would do it naturally by going root 2 over root 2. And then you multiply the fractions across. 1 times root 2 is root 2. Root 2 times root 2 is 2. And we have rationalized the denominator. This is a classic move in trig. Now for 1 over root x, the thing is, I don't know what x is, right? It could be pi, it could be whatever. We normally leave that as is. We normally don't rewrite that. And that's something that I had to realize as a teacher. If you end with 1 over root x, we normally leave it like that because, I mean, x could be pi, right? So this is considered simplified. And I didn't realize until that many years into my teaching career. All right, 1 over root x, you're good. 1 over root pi, well, pi's irrational. You can't make the denominator nice. That's good. All right, so that's with the one-term guys, okay? Any questions about the one-term guys before I get to the two-term guys, which are harder? The two-term guys are harder. Okay, again, I'll focus on denominators. Let's say that I do 3, let's say, over, how about root x? Yeah, okay, this is pretty standard issue. Okay, root x plus h minus root x. Something like that. All right, so rationalize the denominator. Okay. I mean, if this were flipped, you'd rationalize the numerator. It's not so much whether it's the numerator or the denominator. It's whether it has 1 or 2 terms, right? Okay, so this guy's kind of ugly. We have a radical expression with 2 terms. So when we multiply by 1, right, you're not gonna make things nice by doing the copy the way we did over here. We have to multiply by what's called the conjugate of the radical expression, which means we multiply by root x plus h, what? When you write down the conjugate, we flip the sign over here. If that were a plus, this would be a minus, right? Okay, and then root x. And then I forget this too. Remember, we're multiplying by 1. You have to put this twin up on top. And even I forget to do that because it's wishful thinking. I know people hate to do it. I hate to do it. But that twin goes on top. You have to multiply by 1. I mean, you can't just divide by this guy because you feel like it, right? This, we're multiplying by 1, which is legit. Oh, and by the way, don't worry about domain. Do not worry about domain. That's the last thing we have to worry about here. All right? Any questions thus far? Questions thus far? All right, let's proceed. So why do we do this? Why do we multiply by the conjugate? Well, it's based on this principle, this algebra principle. If I have a minus b and a plus b, that's the factorization for what? When you multiply these guys, you get what? You get, yeah, you get a squared minus b squared. Because if you FOIL it, you get a times a is a squared. Okay, the outer product, a times b is ab, but the inner product is the opposite of ab. They cancel each other out, okay? So then we have the first product and then the last product. The opposite of b times b is the opposite of b squared, all right? So this is a squared minus b squared. If you look backwards, that's a factoring rule, right? I don't care what order you put these in. All right. So where are we? Okay, I'll go back to green. All right, equals. That top's ugly. 3 times, parentheses, root x plus h. And remember, it's a plus sign. You're matching the guy on bottom here. It's the plus sign, plus root x. On the bottom, we exploit this rule. It's this, I'll write this out. It's that first guy, the a guy, it's a substitution. It's this a guy all squared, right? Minus the b guy. and that's squared. All right. Now, to make things easier, as a student, you should keep rewriting the numerator, but let's get straight to the point. Let's simplify the bottom here. The square of the square root of x plus h. Let's assume this is non-negative, whatever. What's left? Plain old x plus h. Minus the square of root x, plain old x. Now, if these were switched, I'd really need the grouping symbols, but in this order, it turns out that I don't need the grouping symbols. I'm just subtracting a guy with one term here. So it turns out I don't need these, but put them in first and check. Make sure if you don't need them. Here, I don't need them. What happens? What happens? Goodbye? Goodbye? There you go. Yep. It cancels in an additive sense, right? And I think we're done here, right? Well, I guess I'm done. I made this up. So 3 times this thing. All over h, all right? And if you see any h factors up here, cancel out, All right, but that's an example of rationalizing. This is not a rhetorical question. Did I make any mistakes? I'm not being rhetorical. Did I make any mistakes? Okay. Questions? So, James Harris, did you have any questions about this, or did you want to follow up on this? Okay, thank you. All right, thank you. You're welcome. And this is on YouTube. Yeah, it'll be on the YouTube thing. Let's go in order. I'll save this, and I'll title it. These are good notes for me too. Okay, so let me. Okay, yeah, so 0.10 number 2. Okay, and well, 1F, we just did 1F, right? So 0.10 number 2. All right. Oh, okay, all right. So I'm going in the order in the chat. All right, so let's okay. By the way, okay, so it's 9:05 now, but you're free to go anytime, and I'm willing to stop up at as late as 10:30. All right. Okay, so can we do 0.10 number 2? All right. I hope I can. Okay. So what's the question here? Oh, okay. Oh, actually, I can do this right here. Okay, 0.10 number 2. It's the idea that if you're multiplying by a real number that's not 0, you divide by its reciprocal. Okay, so I can do it right here. X squared. Right now it's being multiplied by 4/9. That's the same thing as dividing by its, what's that R word? Its reciprocal, which is 9/4. Minus, right now the y squared is being multiplied by the 16 after the minus sign. If you're multiplying y squared by 16, you're dividing by what? You're dividing by 1/16. That's all. And the reason why we do this is that we do this when we analyze equations of ellipses. Right. Croy, any questions? I'm sorry if I'm mispronouncing your name. Any questions? 0.10 number 2. All right. I'm sorry. Do you have a phonetic pronunciation for your name? I don't want to mispronounce it. Croy? Okay. Thank you. Like French? All right. Okay. 1F we did, right? That was the monster. 0.94b. 0.94b. Wait, is this? Yeah, okay, 0.94b. Oh, equivalence. Oh, okay. So 4b, again, I can write on here. Remember the basic rule. The square root of x squared, a lot of people say it's x. That's true if x is non-negative. But in general, for all real values of x, you need absolute value. All right? So basically, this is true. This is correct. Where you can substitute x for a minus 4, and that principle applies. The square root of the square of something is the absolute value of that thing. The answer is yes. All right, questions? All right. 0.91G. Yeah. Oh, yeah, that's right. That's right. We're going to do that one. That was the absolute value one. Yeah. So yeah, we're talking about absolute value problems, right? Okay. So this is a good follow-up, actually. I'm excusing the fact I have a bad memory. All right. That's right. Okay. 0.91G. All right. Actually, it's not too long. The thing is, you have to understand what's going on here. And the key assumption is we're assuming that x is less than 3. Otherwise, see, this thing would be simplified if we didn't have this assumption. But we now have this assumption, right? Now, here's the key idea. Okay. We're given that x is less than 3. All right. If we subtract 3 from both sides, we have x minus 3 is less than 0. Or if you don't want to think of that in terms of like the algebra, imagine plugging in values of x like 2, 1, or 2.9, right? Well, you can see that if you plug in values like 2.9 or even 2, you're going to get a negative value for x minus 3. The bottom line is x minus 3 is going to be negative, all right? Now, here's the idea. The absolute value of a negative value is equal to its what? The absolute value of a negative value is equal to its opposite. Its opposite. For example, the absolute value of negative 7. Negative 7 is negative. The absolute value of negative 7 is its opposite, positive 7, correct? All right. So what am I saying here? I'm now going to finally rewrite this problem. I will actually rewrite it. The absolute value of x minus 3 over x squared minus 5x plus 6. Under the assumption that x is less than 3. I know then that this thing here is negative in value. Remind me, folks, the absolute value of a negative value is equal to its what? The absolute value of a negative value is equal to its opposite. I'm going to put a red arrow. This is what people miss. All right. If x is known to be less than 3, or is assumed to be less than 3, the absolute value of x minus 3 is equal to the opposite of x minus 3 by the piecewise definition of absolute value. Okay. On the bottom, it's old school factoring. Okay. X minus 3 is one factor. X minus 2 is the other. The order does not matter. And then we can divide. We're dividing a pair of opposites. I'll cross this all out. And the result up here will be negative 1. Where if I cross out the negative sign there, I'll put it here. Right? So the final answer will be, we like to pop out the opposite sign outside of the fraction. The opposite of 1 over x minus 2. Or if you want to be even more efficient, if you multiply by negative 1, that's the same as dividing by negative 1. And we can use the fact that the opposite of x minus 2 is 2 minus x. So this can also be rewritten as 1 over 2 minus x. And some people might even want to remind people of the restriction if x is less than 3. Okay, we might want to remind people of that restriction. Okay, I'm putting the answer in red here. Yeah. All right. Any questions about that? Any questions? Any questions? All right. I'm following in order. See, that was 1G. All right. Next is 10.15, number 1. Any questions about this before I go on? Okay. 0.15.1.
Yeah. 0.51. I was the one that suggested that. I got a pretty simple answer, and I can't see why it wouldn't work. Would it be okay if I write it out, maybe?
Okay. Derive the formula.
Oh, okay.
Oh, to a pair of triangles. Right.
Yeah, actually, could you just show us how to do this?
Yeah, let me show you. Yeah, what? Okay, so I'll just draw a sketch trapezoid here. All right. So here's a sketch trapezoid. Okay, and I'm gonna break it up into a pair of triangles. So this base is B sub 1. This base is B sub 2. Height in green. All right, so you agree with the notations. All right, so here's the idea. Here's, in purple, here is area number 1. In purple, here is area number 2. All right, so the area of the trapezoid equals the sum of the two areas. Area equals, what's the area of triangle 1? 1/2 base times height. 1/2, its base is B sub 1. The height is H. In fact, it's the height for both triangles. Plus the area for triangle 2, 1/2 base times height. 1/2, the base is B2 for all this. The base is B2. Same height as the trapezoid and the other triangle. I can then factor out the 1/2, factor out the H, and I get this. And there are various ways you can write this. In the notes, I may have put this over the 2, right? I put the 2 underneath. Yeah. That's the idea. Any questions? Any questions? So I wanted to focus on people using the formula for the area of a triangle to build up the area of a trapezoid. Questions? Questions?
No questions here. That makes sense. Thank you.
Oh, you're welcome. Yes.
I think I just misread the prompt a little.
Well, it's tricky, right? Sometimes number 1's the trickiest. Oh yeah, I don't waste your time. No, the homework is carefully designed by me to not waste your time.
Yeah, I've noticed.
Yeah, I don't like. I mean, I know I have Alex, but I don't like random systems going do this, do that, do that. It's random. All right. 0.91b. 0.91b. Right. Well, I'll save this one. Okay. 0.91b. Yes. Actually, I did this in the YouTube video. I believe I did this in the YouTube video. So I could come back to this later, but I believe I addressed this. I'll give you a hint, though. I'll give you a hint. T cubed plus 27. That's a sum of 2 nice what? T cubed, 27. It's a sum of 2 nice cubes. It's a soap problem. It's a soap problem, right? But of course, we're welcome to go back to this. Hey, I'm going to go at 10:30. So, if we have time and there are no other questions, I'll come back to this. But right now, you can check the YouTube video. I think it's in there. But let's put this on the side. We may come back to this. All right. And please correct me if that's not the case. I think that is the case, though. And I can come back to this. Oh, that's the last one. Well, okay, so let's do this. I mean, I'm willing to do this one, but were there any other questions that anyone would like me to address? Or if you want to hang out with me, hey, I'm here for the next hour or 10 minutes, so I can work on 1B. That's fine. Oh, I see. So I see a no. Let's do the new one. No, let's do 0.10 number 3 because I think this is on YouTube. So let's do 0.10 number 3. Okay, but we're gonna do this one. I don't think we did it last time. Oh yeah, that's right. Okay, and this was a tricky problem, right? So fill in the blanks. And later on, I guess you could use long division, but here's a clever way of using compensating. All right, so here's the idea. X squared over x squared plus 9. Whoops. I want to make a 1. I want to make something that's going to end up being 1, which means that I want a quotient of twins eventually. So we have x squared plus 9 on the bottom. If I want a 1 over here, I'm going to put this guy's twin up on top. X squared, and then plus 9. And you would agree that x squared plus 9 divided by itself would be 1. But now wait a minute. I can't just add 9 to the top because I feel like it, right? I have to pay for it. I have to compensate. And I cannot do it by adding 9 to the bottom. That's like saying that 2/3 of a pizza equals 1/2 of a pizza or 3/4 of a pizza. That's a crazy diet. You're not allowed to do this. But what can I do? If I add 9 to the top, what else can I do to the top? What undoes adding by 9? What undoes adding by 9? Subtracting by 9. Subtracting. So basically, we're adding by 0, right? Now you agree, these are equivalent. This is legal. I can take the top, and I can add 9 and subtract 9. You're agreeing that I'm not changing the value of the expression, right? We're good. I'm just changing the form. Okay, and why am I doing this? Because my goal is I want that 1 there. Believe it or not, we're going to follow similar strategies when we verify trig identities. Remember that stuff? I'm going to break up the fraction. I can break up the fraction at that minus sign. X squared plus 9 over x squared plus 9. That's a big old minus sign. And we have 9 over x squared plus 9. What's x squared plus 9 divided by itself? That's 1. That's where a 1 comes from, right? That's where a 1 comes from. Minus this over here. All right. Any questions about that? It's not so much that you're going to do this particular procedure in calculus, but it's a good way of checking the mastery of your algebra. And students always ask me about this one. Any questions? Any questions? You're welcome. Yes. Any other questions? Any other questions? In fact, what I could even do is I could even grab my video. I can show you the video for for 0.9 what? Or for the perfect cubes one? Oh, okay. On 0.13 number 5, why is the answer over 4? Wait. Oh, yeah, I think I can answer this. Okay. These points are at the endpoints of a diameter, right? So it's like here's -5, -1. Here's -5, right? They're the endpoints of a diameter. Whoops. But here's the thing, though. In the equation for a circle, you don't want the diameter, you want the radius, right? So as part of the process, you want to find the center. And then you can find the radius, or just use the fact that the radius is the diameter over 2. I better spell it out. A diameter instead of distance. Diameter over 2. So, Cry, I bet you what happened was that instead of taking the radius, you took the diameter. Remember, to get when you get the distance between the 2 points, you're getting a diameter, but you have to divide it by 2 to get the radius. And I must say that that's a very common error on the homework and on tests when I give this kind of problem on tests. Okay, so I'll bet that's what happened. Check on that. Okay. So I think Tessa's confirming that she'd like to see a replay of some of 2 cubes. So I may as well play what I had before. Okay. All right, let's go to the video. Go back to the tape. Oops. Uh, okay. But these are the monsters. If you want to see the, yeah. Right here, right here. Yeah, it might have been, yeah, it's the very first problem. Hey, very first problem.
Really simple, but I just can't get it down. It's 0.91b, and I know that you just factor the top and you take out t plus 3, but I don't know how you get the other part of it.
Okay, 0.9, is that right? Okay.
Yeah, I got the answer and I worked backwards and it's simple, but I just I don't know why my brain can just not do like easy factoring right now.
And you can tell I already worked on this with a student, so other students have asked about this too. All right. These are my answers again. I need the. So that's.
Even better yet.
Oh yeah.
Even better. You know what? On YouTube, I have the caption version. That's gonna be even better. Let me go to my YouTube. Yeah. Let me go to my YouTube because it's captioned. I think it's captioned. That's gonna be awesome. Okay. It'll be a separate session. Sure. All right. So no private talk. All right. Well, I know some students might be shy, but there's no reason to be shy. I mean, if you have a question, lots of people would have questions. All right. So let's keep it on then. All right. So first come, first serve.
I have a question. It's really simple, but I just can't get it down. It's 0.91b, and I know that you just factor the top and you take out t plus 3, but I don't know how you get the other part of it.
Okay, 0.9, is that right? Okay.
Yeah, I got the answer and I worked backwards and it's simple, but I just I don't know why my brain can just not do like easy factoring right now.
And you can tell I already worked on this with a student, so other students have asked about this too. All right. These are my answers again. I need the. So that's. Oh yeah. These are the questions, right? And these are the answers. All right. Yeah, it's just that the questions were short. All right. But the solutions can be long. Okay, so 0.9 B. Did you say B?
Yeah.
B. Yeah. Okay. So all right. So I circled the appropriate pieces. So this is 0.91 B, and I circled the appropriate pieces here. The key thing is the top. On the top, we have the sum of two nice what? We have t cubed and 27. Those are both perfect cubes, right? Okay, so that's correct. The sum of two cubes. So it's a SOAP problem. It's a SOAP problem. All right. And by the way, I do welcome student responses. Okay, so students, any brave souls, how do you factor this? We factor it as a binomial times a trinomial. What's the nice binomial factor if you have t cubed plus 27?
I know it's t plus 3 because you want to cancel the numerator and the denominator, but I just don't know the trinomial to it.
Oh yeah,
I don't know how to get that.
That's clever strategizing as a student, but I want to explain why it's legit, right? So basically, we're taking the cube root of t cubed, right? The cube of t is t cubed. The cube root of 27 is 3, right? 3 cubed is 27. S for, why am I saying S? S for same sign. Same sign as what's here. Okay, so you know why t plus 3 is correct. Okay, aside from the practical issue, yeah, we want to cancel, but that's too practically thinking. All right, now the trinomial factor here, the trinomial. Okay, so it's gonna be t squared, correct? And then I want to say O. O for what? O for the opposite sign, minus. Okay, so this here is a plus sign. This here is the opposite, the minus sign. All right. Right, and the student's correct, right? So the next piece would be 3t. You take the straight product, 3t. 3 times t is 3t, all right? Oops. 3t. And then to end SOAP, it's AP for what? AP is for always positive or always plus. And the square of 3 is 9. So the student's correct. All right. So that's the hard part. That's 80% of the problem, right? Okay. And as you've observed, right, we can do what?
Cancel.
Yes, we can divide out. Okay, these divide out to 1. It's good practice to put a 1 down there, you know. Okay. But in the end, we're basically going to get this trinomial piece. T squared minus 3t plus 9. And by the way, we're hiding a restriction. T cannot be what number? What makes the bottom equal to 0?
-3.
-3. That's a hidden restriction. It's not critical. It's not like I take off 10 points on a test for that, but in order to make it perfectly equivalent, we should note that. All right, so look at the answers here. Yes, the answer to B is that trinomial, t squared minus 3t plus 9, with the hidden restriction that t cannot be -3. Any questions? Okay, well, let me ask, did you understand this, or are there any questions about B?
You know, I understand it now. I just didn't. I forgot SOAP, so now it's perfectly understandable.
Well, I understand,
another problem.
Yeah, almost no one saw SOAP before today, unless before this class, unless you took pre-calc before. So no, a lot of people. This is new. Oh yeah.
Yeah, I took pre-calc, but it was like 4 years ago, so I don't remember that.
Yeah, was it in high school?
Yeah, in high school.
Yeah, let me tell you, man. College pre-calc is nothing like high school pre-calc. No, this is a challenging class. All right, so we're good on B, and I have another request. Okay, so yeah, that was helpful to me too, just having the conversation going. Yeah, these videos are really helpful for me too. Lets me save my voice too. All right, and this is online. It's on YouTube. I got a lot of good stuff on YouTube. All right, what's next?
All right, what's next? Okay, well, it's 9:32, and you folks are conscientious, great students. I'll stay for another hour. Okay. All right. So 12.1a. Okay. This is 10.3. All right. 12.1a. Oh yeah, yeah. Inequalities. I really flew through that stuff in class. All right. So we start with that. Negative 2x is less than negative 2x. I could type this one out. Negative 2x is less than 5x plus 21. All right. Okay, so different ways of doing this. I think a lot of students would subtract 5x. Negative 2x minus 5x is negative 7x. Oops. Is less than 21. So I'm subtracting 5x from both sides. Negative 2x minus 5x is negative 7x is less than. We kill the 5x guys over 5x and negative 5x. They add a 0. We have the 21. Negative 7x is less than 21. All right. But now be careful. Be careful. We now divide both sides by negative 7. Negative 7x divided by negative 7 is x. 21 divided by negative 7 is negative 3. What's the catch? Flip. Remember that when you multiply or divide both sides of an inequality by a negative number, or if you're switching sides, you must flip the inequality symbol. So that's the key observation. And I know that I really had to fly through both point 11 and point 12 in class. So yeah, you're kind of reviewing the notes for that. And then you would write down the corresponding step builder, graphical, and interval form. But up to here, so if you believe me up to here, would you like me to go in and talk about these forms, or are you okay here? Okay, all right. But again, since the solution of this would be a solution set, then you'd want to write either step builder form, graphical form, or interval form. I want all three in the problem. Okay, but this is the key part where people would tend to make a mistake. Flip the symbol. Again, when you do that, if you're multiplying or dividing both sides of an inequality by a negative number, or if you're switching the sides. If you're subtracting, you don't flip. Okay, I'll keep going. Or if you want to say to me that if you want me to wait for like 5-10 minutes for you to gather some thoughts, that's fine too. Let's see, any questions? So what do you think? Would you like to take a 10-minute break again, and then at 9, maybe at 9:50? At 9:50, I can come back in and see if anyone has any more thoughts. Want to do that? So let's pause now. Okay, let's I'll return at 9:50. Re record. Okay, gotta remind me. Record. All right. So let's come back at 9:50. I'll take a brief walk. All right. Okay. So hi everyone. I had a flag that my connection was a little unstable, but I will go on. Okay, but if you cut out, I got a warning on my end. Okay, so anyway, 0.55b. Okay. All right, we're back. And let me know if the connection is hazy. All right. Okay. Right. Yeah. So that's an exercise in fractions. Right. Okay. No joke. A lot of people have trouble with this. All right. So let's first rewrite this. I'll do it directly. So star, the guy I'm giving you, right, equals. Right. So how can you rewrite this as a power of x? Right. It's going to be x to the. It's going to be 3 over 4, 3/4. Right. Times the cube root of x, that's x to the what? That's x to the 1/3. I am recording, right? I'm recording, all right. All over x to the -2. In fact, to save time, bear in mind, the x to the -2 can hop up as x squared. Okay, and observe that 0 is excluded from here anyway, right? Okay, well, yeah. And also negative values are excluded by the 4th root here. All right, so really I end up with that, right? So x to the 3/4 times x to the 1/3 times x to the 2nd. This guy kind of rolls up as x to the +2, all right? Any questions so far? Any questions? Okay, I hope my connection's still good. All right, now when we multiply powers of x, what do we do to the exponents? When we multiply powers of x, what do we do to the exponents? We add them. 3/4 plus 1/3 plus, I'll write this as 2 over 1. And no joke, this is a hard part for people, fractions. Right, common denominator, right. This gets people. Okay, I'll complete. The common denominator is 12. So I'm going to focus on the exponent here. Common denominator is 12. Four times 3 is 12. 3 times 3 is 9. So 3/4 is 9/12. I'm multiplying by 3 on the top and the bottom. Again, I'm multiplying by 1, right? 3/4 times 3 over 3 is 9 over 12. Similarly, if you multiply top and bottom by 4, you get 4/12. 1/3 is 4/12. Multiply top and bottom by 12, all right? You get 24 over 12. And we're adding 24 over 12. When we add fractions, remember, we keep the denominator. We don't add, we keep the denominator, the common denominator, 12. 9 plus 4 plus 24, you get that weird number, 37. I know this because I've worked on this with many students before. Answer is x to the 37 over 12. Okay, and you might want to remind people that we restricted x to be positive. In particular, x cannot be 0 because it's not evident here that x cannot be 0. All right. But yeah, students have a hard time with that. Fractions. All right. Um, okay, the 0.8 problems. Okay, so what's your favorite one or least favorite or A? All right, let's do it. 0.81A. All right. I'll write it out. Okay, so we have 2x to the negative fifth plus 4x to the negative 3 plus 2x to negative 1. Okay, we can factor out a 2. That's not too bad. All right. We can also factor out x to the what? Remember, we factor out the power of x with the least exponent. What are the exponents? Negative 5, negative 3, negative 1. Correct. Negative 5 is furthest to the left on the real number line. This is our GCF. All right. So now let's get the other factor. Well, this divided by itself is 1. All right. Plus, for this term, 4 divided by 2 is 2. X to the, all right. Over here we start with a negative 3. When we factor, we divide. When we divide, what do we do with the exponents? When we divide powers of x, what do we do with the exponents? Well, we subtract, right? But you're right that negative 3 plus 5 is 2, right? So we ultimately say that negative 3 plus 5 is 2. That is right. Plus 2 divided by 2 is 1. And then x to the, all right, negative 1. Take away the negative 5. We'll write that. Okay. So you start off with a subtraction, but you're correct that you end up adding. All right. Questions? 2x negative fifth. Okay. We have a couple steps. Quantity 1 plus, you said it, 2x squared. You're right. Plus x to the fourth. I'll make two more observations, and then you should be okay. First of all, what can you do with the x to the negative 5? What can we do with that? Basically, we can put them in the bottom as x to the fifth, right? This thing here, it is a PST. Do you know what a PST is? Yeah, you have to type it out. It's a perfect square trinomial. I type fast, but it's a perfect square trinomial. So if you get those two observations, I think you'll be okay. Would anyone like me to proceed? All right. Okay. Anyone else want me to proceed? I'll save this. All right. So anything else, or anyone want me to proceed? Anything else? All right. Anything else? So we can do it again. So we can take another 10-minute break as you collect your thoughts. 10-10. Why not do this? Okay, so 10-10, I'll be back. All right. See you in 10 minutes. All right, back in business. Okay, Corey got a couple there. All right, so let's take a look at those. let's see here. Okay. All right, so 0.10 number 4. Oh, I wonder if I can write on here. Oh, this one. Okay, now number 4. This isn't so bad. It's a concept problem. So basically, if you have an expression, right, and you do this in, it's a technique in calculus. If you have an expression and if you multiply by 12, okay, now you can't just multiply by 12 because you feel like it. You have to pay for it, right? Now it is legal to multiply by 1. So if you're multiplying something by 12, what can you do to balance that out? What can pay for that? Correct. If you're multiplying by 12, you can pay for that by dividing by 12 or multiplying by 1/12. That's all. It was that concept. This comes up in the use substitution technique for integration. Right. Yeah, some of these, it's like, some of these you can follow your intuition, but you're wondering, why am I doing it? All right, so 0.119. Okay, oh yeah, okay. I didn't have much time to discuss this. Solve the absolute value equation and interpret your solution in terms of distances along the real number line. All right, so the absolute value of x plus 4 equals 3. Now we could do a basic substitution. Wait. Oh, that's 8. Sorry, 9. Oh, okay. Oh, did you get 8? That's where you set this equal to 3 and -3. Oh, okay. Sorry. No, 9. No, there's no work here. See, that's a negative number. Can absolute value be negative? No. Solution set's the empty set. It's a trick question. Okay. So it was a tricky observation, but there's really no work here. There are no real values for x that can make absolute value negative. All right. So in both cases, a little tricky, but short solutions. Basically answer only. All right, anything else? So can you do one of the 0.11s, 5 or 6? Let's do 6. I'll do the harder one. All right, so I can just erase this. Okay, so doing a rational equation. So, all right, so I'll do number 6. All right, now I'm going to multiply both sides by x plus 1. All right, so I get x squared minus x equals 2. Now, one thing you have to worry about, though, is that when you multiply both sides by x plus 1, you're hiding a restriction, right? Because x cannot be what number? X cannot be what makes the bottom 0? -1, right? So there's a restriction you're hiding as you solve this equation, all right? Okay, now we do have an x term, so it's best to isolate 0. I'm going to subtract 2 from both sides. Remember, say subtract, not move. X squared minus x minus 2 equals 0. Old school factoring does work. X minus 2 and x plus 1 in either order. So does the solution set consist of 2 and -1? What do you think? Is that the solution set? Is that the solution set? The answer is no. X cannot be -1. We have to reject this tentative solution. There's only one solution. His name's 2. Right. So this is one case where the whole hidden restriction thing actually does bite you. Oh, you're welcome. Yes. Because before, when we were simplifying expressions, I would just go, yeah, I hope you notice this. But actually here, it had a real impact, a literally real impact on the solution set. Yeah, yeah. So that's the problem with these rational equations. You got to be careful when you get a 0 denominator. That's why checking can help, right? So when in doubt, if you're afraid that you're overlooking something, check your solutions. Like for radical equations, it's very typical to check solutions. All right, anything else? We're at 10:16. I'll keep it to 10:20. If there's nothing by then I'll end this. But yeah, so let's see if there's anything more. Oh, you're welcome. Yes. So I'll keep this open until at least 10:20. If you have a question, let me know. No point taking a 10-minute break now, right? I mean, so let's go to 10:20, see if anything comes up. All right. You're welcome. Yes. And thank you for sticking around. That's very strong commitment. I appreciate that. Thank you. Yes. Good night. Good night. Good night and good luck. All right. End recording.